We are now going to discuss linear approximations. If you haven't watched the video about differentials, I encourage you to watch that first. In that video about differentials, we said that when our dx, when our change in x is small, we can approximate our delta y, our change in y along the graph of a function, with that differential dy. What that means when we're doing that approximation, we're actually using our tangent line to estimate the value of the function when we are close to that point of tangency. This concept of using a tangent line to create an approximation is called a linearization. So the equation of a tangent line to the graph of a function, so equation of the tangent line to y equals f of x at x equal a, is y equals f of a plus f prime of a times x minus a. That's just my point slope formula written as a slightly different form. The m is my derivative. We know the derivative gives a slope of the tangent line. And then the y1 was just moved to the other side of the equal sign, so that's why we have this f of a on the right-hand side. So this tangent line is also called a linear approximation or a linearization of this function at x equal a. Let's find the linear approximation of f of x equals the square root of x plus 3 at a equal 1. So the linear approximation of a function is just its tangent line. To find the equation of the tangent line, we first have to find the slope or the derivative. Square root of x plus 3 is x plus 3 to the 1/2. So I brought down the 1/2, I got 1/2 x plus 3 to the negative 1/2. And then I do have to use the chain rule. I have to multiply by the derivative of the inside. The inside is x plus 3. Well, that just has a derivative of 1. So I'm going to write my derivative as 1 over 2 x plus 3 to the 1/2, or 1 over 2 x square root x plus 3. To get my slope, I'm going to plug x equal 1, that's the a value here, x equal 1 into that derivative. That becomes 1 over 2 times square root of 4, or 1/4. Then, for the point of tangency, we're working at a equals 1, or x equals 1. So the y value for my point of tangency, I'm going to take that 1 and plug that into my function. Square root of 1 plus 3 becomes root 4, or 2. So my tangent line is y minus 2 equals 1/4 times x minus 1. I can bring that 2 over, and then I have y equals 2 plus 1/4 times x minus 1. This is my linearization. And you can change that y to an L of x if you want to use function notation. You don't have to do that, but I'm going to use L of x to stand for my output or my y value. So linearizations in tangent lines are the same thing. The second part of the problem is asking us to use our linearization to estimate the value of the square root of 3.98. So the first thing I need to think about is if I wanted to find the square root of 3.98, what number would I plug in for x into my original function? Well, if I replace the x with 0.98, then f of 0.98 would give me square root of 3.98. So I'm basically trying to estimate the value of f of 0.98. I can do that with my tangent line by finding L of 0.98. So I'm going to take the 0.98 and I'm going to plug that in for x into my tangent line. I get 2 plus 1/4 times 0.98 minus 1, or 2 plus 1/4 times negative 0.02. Final answer, 1.995. And you can check with a calculator. This is actually really close to the actual value of the square root of 3.98. And so graphically what we've done is this curve in red, that is the graph of my square root function. In blue, the line is my linearization or my tangent line. the point of tangency was 1, 2, and you can see at that point of tangency, the function and the tangent line are the exact same. And when we're really close to that point of tangency, so for example, if we move over to 0.98, we can't really even see that on this graph, that function and that tangent line are really close together, and the tangent line is a great approximation for the function. Here's another example. Use a linearization to estimate the value of 1 divided by 10.1. This time they didn't give us a function or a point of tangency, so we're going to pick something that makes sense for this problem. I'm going to use the function 1 divided by x. So I'm going to let f of x equal 1 divided by x, and I can use that function to approximate 1 divided by 10.1. So that's my function. Then I need to pick a point of tangency, a place where I want to create my linearization. And what you want to do is pick a nice number that's easy to work with, that is close to the value you want to find. So notice I want to see what is 1 divided by 10.1. So I'm going to linearize around 10. 10 is a nice whole number, it's easy to work with, and it's pretty close to 10.1. So what we're going to do is come up with our tangent line to the function f of x equals 1 over x at x equal 10. So I'm going to start with my derivative. 1 over x is the same as x to the negative 1. So that derivative would be negative x to the negative 2, or negative 1 over x squared. To get my slope, I'm going to plug 10 in for x, so negative 1 over 10 squared, or negative 100 is the slope of my tangent line. My point of tangency is at x equal 10. The y value for that point of tangency is going to be f of 10. So f of 10, plug 10 in for x, I get 1/10. That means my tangent line is y minus 1/10 equals negative 100th times x minus 10. We can solve for y, move that 1/10 over, and again, I'm going to use function notation and replace that y with L of x. So here's my linearization. L of x equals 1/10 minus 1 over 100 times x minus 10. Finally, I want to approximate 1 over 10.1. So I'm going to take 10.1 and plug that into my linearization. The idea is that the linearization at 10.1 should be really close to the function value at 10.1. So putting 10.1 into my tangent line, 1/10 minus 1/100th times 10.1 minus 10, that is 0.099. And again, you could check in a calculator. This is actually really close to the actual value of 1 divided by 10.1. And that is my last example. So please let me know if anything in this video is unclear.